Welcome back, everyone, to the deep dive. This time, we're going deep into the world of RNNs, recurrent neural networks.
Oh, yeah, RNNs.
You guys sent in a paper titled, Were RNNs All We Needed?
Ugh,
By Leo Feng. And
I saw that one.
it's a pretty bold question, right?
Yeah, definitely an attention grabber. Makes you wonder if we maybe overlooked something.
Like, were we too quick to jump on the Transformer bandwagon?
That's what the paper seems to suggest. I mean, for a while there, it felt like Transformers were the answer to everything.
Mhm.
RNNs kind of got left behind.
So, like, what happened? RNNs used to be all the rage. What changed?
Well, the original RNNs, the vanilla ones, had some issues. Like
Mm.
the vanishing or exploding gradient problem made it tough for them to learn long-range dependencies and
Right,
sequences.
right. And then came LSTMs and GRUs.
Exactly. Those were designed to fix those problems, and for a good while, they were the go-to for anything involving sequences. But they had their own quirks, mainly that they were computationally expensive, especially when sequences got longer.
And that's where Transformers came in, right?
Yeah.
Because they could process sequences in parallel.
Bingo. Speed was king, and transformers were much faster to train.
So this paper is saying, hold on, maybe we dismissed RNNs too soon.
Yeah, that's the gist of it. And they're not just saying, hey, let's go back to LSTMs and GRUs. They're proposing something even more radical, simplifying them further.
So like less is more.
That's the idea. They call them min LSTM and min GRU.
I gotta admit, I'm a bit skeptical. How can you simplify something like an LSTM and still expect it to work well?
Well, it's not just about blindly removing stuff. They did it strategically. They got rid of the hidden state dependencies from the input, forget, and update gates, streamlined the process, so to speak.
So they made them leaner, but does it actually make a difference? Like, are they really that much faster?
Oh, the difference is huge. For sequences of 512 tokens, MinGRU trains 175 times faster than a standard GRU.
Wait, 175 times?
Yep. And MinLSTM is even crazier, like 235 times faster, and they need way fewer parameters too. Sometimes MinGRU uses only 13% of the parameters of a regular GRU. We could be talking about going from years to days for training.
That's insane. But I'm still stuck on this whole simplifying thing. Don't you lose something by doing that? Like the ability to learn complex patterns.
It's a valid point, but get this. When you stack multiple layers of these minimal models, you actually get more complexity and time dependency. It's like building with Legos. You start with simple bricks, but you can create some pretty amazing structures.
I see. So they tested these minimal models on something called the selective copying task. What's that all about?
It's a test to see how well a model can find specific information in a long sequence, like finding a needle in a haystack, but for AI.
How did MinLSTM and MinGRU do?
They aced it. They were some of the very few models that could solve it consistently. Other models, much more complex ones, just couldn't crack it.
Impressive. So they're not just fast, they can actually handle some tough problems.
Didn't they test them on other stuff too? Like reinforcement learning.
They did. They used the D4RL Mujoko benchmark where you train agents to control simulated robots.
Yeah.
They actually beat the Decision S4 model and were right up there with some of the top performers like Decision Transformer, Aaron, and Decision Mamba, even outperforming some in certain cases.
Wow. So even in a field that loves complexity, these simplified RNNs are holding their own. What other tasks did they test them on?
They also did a language modeling task with a character-level GTT model on Shakespeare's works. They compared it to Mamba and, of course, Transformers.
So how'd they do?
All of the models ended up with similar test law scores, meaning they were all good at predicting the next character in a sequence, but MinGRU and MinLSTM got there way faster, needed far fewer training steps.
So it's not just about accuracy, it's about efficiency too.
Exactly, and that brings us back to the big question in the title. Were RNNs all we needed? It's a bold claim, but their research is making us rethink things. Like maybe we were too quick to move on from these outdated models.
Sometimes the answer is right there in front of us, just waiting to be rediscovered.
This is amazing. I have so many more questions, though. Like, how do these minimal RNNs compare to other recent recurrent models? And what does all this mean for AI in the real world?
Great questions. But before we go there, maybe we should talk about some of the other approaches to efficient sequence modeling that have been popping up. Stuff like state space models and recurrent attention mechanisms.
Ooh, that sounds interesting. All right, let's dive into that.
So state space models and recurrent attention, you want to dig into those?
Yeah, for sure. But maybe first, like a quick overview. What are we even talking about here?
Okay, so state space models, SSMs for short, think of it like tracking a pendulum. It's got a position and a velocity, right? That's its state. SSMs try to model sequences as systems that change over time, like that pendulum swinging back and forth.
Okay, I kind of get that, but how does that apply to, like, words and sentences?
Good point. It's about the meaning, the context. Think of the state as the meaning that's being built as you read a sentence. Each word changes that state, adds new information, shifts the understanding. SSMs give you a way to represent that mathematically.
So instead of a pendulum, it's the meaning that's swinging back and forth.
Exactly. And what's really cool is the paper points out that SSMs and MinLSTM in GRU have a lot in common. Like Mamba, a popular SSM, uses a formulation that looks a lot like the math behind those minimal RNNs.
So even though they come from different places, they kind of end up in the same spot.
Yeah, it's like they're converging on similar ideas. Early SSMs had a problem, though. Their transitions, how the state changes, were fixed. They didn't depend on the input.
So no matter what the word was, the meaning would change in the same way. That seems kind of limited.
Right. And that's where Mamba's S6 variant came in. It made the transitions input dependent. So now the way the state changes is sensitive to the actual word being processed, way more flexible.
Okay, that makes more sense. So we've got SSMs. What about recurrent attention? I thought attention was a transformer thing.
It is, but researchers have found ways to use attention in recurrent models too.
So they're combining the best of both worlds. Sequential processing with that focused attention.
You got it. The paper mentions ARIN as an example. It can be trained in parallel or unrolled sequentially, flexible depending on what you need.
This is getting pretty complex. Simplified RNNs, state space models, recurrent attention. Are they all just competing, or is there something that connects them?
There's actually a common thread running through many of them. The parallel scan algorithm.
Okay, what's that, and how does it fit in?
It's a way to make things run in parallel. Instead of going step by step, you break the problem into chunks that can be processed at the same time. That's why MinLSTM and MinGRU are so fast to train.
So like having a team of workers instead of one guy doing everything.
Perfect analogy. And it's not just theoretical, it's making a real difference in these new recurrent models.
This makes me wonder, if all these different approaches are using similar ideas, does that mean we're thinking about AI differently now?
Maybe it could be that we're moving away from always inventing new things and focusing more on optimizing what we already have.
So instead of complexity, it's about finding elegance in simplicity.
Could be. But it's still early days. We need to see how these models do on bigger data sets and harder tasks.
Right, and they probably have their own limitations too. What are some things to watch out for?
Well, even though they're minimal, the math behind them is still pretty complex. They need to be tuned carefully.
So we still need experts who understand all the details. It's not just set it and forget it.
Nope. And like any machine learning model, there's the risk of overfitting. The model might just memorize the training data and not do well on new stuff.
It's like studying for an exam by just memorizing the answer. It doesn't really mean you understand the material.
Exactly. So we need to make sure these models are really learning, not just memorizing. And we need to watch out for biases in the data that the model might pick up.
So lots of promise, but still work to be done. What are some of the big challenges researchers are facing?
Scaling is a big one. Can these models, which work so well on small tasks, handle the huge data sets used for large language models? That's going to take some clever algorithms and maybe even new hardware.
It's like taking a recipe that works in your kitchen and trying to cook for a whole city.
Right. And besides scaling, people are also looking at ways to improve the architecture. Maybe by combining ideas from other models.
So this is just the start of a new chapter for RNNs. And who knows what's going to happen next.
That's what makes it so exciting. It's all about discovery and pushing the boundaries.
Well, on that note, I think it's time to shift gears and talk about what all of this means in the real world. What are the practical implications of these findings?
That's a great question and leads us into part 3 of our deep dive.
All right, so we've really dug into these simplified RNNs, but I'm thinking about our listeners, and some of them might be wondering, okay, but what does this actually mean for me?
It's a good question. Like, how does this fancy AI stuff translate into something I can actually see and use?
Exactly.
Well, think about chatbots. You know, those things you talk to online for customer service or whatever. They need to understand what you're asking, even if it's complicated, or you type a whole paragraph.
Right, right.
With these simplified RNNs, companies could train those chatbots way faster, use less power, less equipment, and the chatbot could be, like, smoother, quicker to respond, more natural to talk to.
So better chatbots for everyone. Faster, cheaper to develop and better to use.
Got it.
Hmm.
What about other things, though? Like, I know RNNs are used for stuff like translating languages or summarizing text.
Oh, yeah, absolutely. And remember how well MinLSTM and MinGRU did on those language modeling tasks? That means we could see some big improvements in those areas, too.
Like, what kind of improvement? Well, for translations, they could become more accurate, but also more nuanced, like capturing the style of the original language better. And summaries could be better at getting the gist of a long document. Heck, we might even see AI that can write different kinds of creative text formats, like poems or scripts.
Wow, that's pretty mind-blowing. It's like AI is getting closer and closer to what humans can do.
It is. And it's not just about language either. Think about analyzing data that changes over time, like stock prices or health records or weather
Oh,
patterns.
right, time series analysis.
Exactly. These efficient models could analyze way more data, find those hidden patterns, and make better predictions.
So we're talking about like spotting market trends early or getting more personalized medical diagnoses or even predicting extreme weather events more accurately. This could be huge.
It really shows how AI is becoming more and more powerful. But, with great power comes great responsibility.
Yeah, definitely. We need to make sure AI is being used ethically. But let's get back to these models for a sec. We've talked a lot about what they're good at. What about their limitations? Where might they struggle?
Well, even though we call them minimal, they're still pretty complex under the hood. Tuning them to work their best is not easy.
So we still need those AI experts to make sure they're being used right.
Yep. And there's always the risk of overfitting, like we talked about before. The model might get too focused on the specific data it's trained on.
Right, so it might not work well on new data it hasn't seen before.
Exactly. So we need to be careful and test them thoroughly, make sure they're really learning, not just memorizing.
So lots of potential, but still some things to watch out for. What are some of the big challenges researchers are working on now?
Scaling is a big one. We know these models work great on smaller tasks, but can they handle the massive data sets used for things like large language models? That's going to be tough.
Like trying to use a small kitchen to cook for thousands of people. You need bigger equipment, a different approach.
Exactly. And then there's improving the architecture itself, maybe by combining ideas from other models. It's an ongoing process.
So the story of RNNs is just getting started. There's still so much to explore and discover.
And that's what's so cool about this field. There's always something new around the corner.
Well, that about wraps up our deep dive into the world of RNNs. But before we sign off, I want to leave you with a question to think about. Where do you see these simplified RNNs going? Will they become the top dog in AI again? Or will they work alongside other models, each doing what they do best?
It's a question that only time will tell, but one thing's for sure, it's going to be an exciting journey filled with incredible breakthroughs.
Thanks for joining us for this deep dive. Until next time, keep that AI curiosity alive, folks.